Hi everyone, and welcome to our video on limits at infinity. So limits at infinity determine the end behavior of a function, and what we'll be doing is looking at a limit as x goes to plus or minus infinity, so one or the other. So we say it does the end behavior, so as x goes to infinity, that means that's the far right of the graph, or far right of the function. And then if x goes to negative infinity, that's the far left. Let's just say far left, we'll abbreviate. Okay, so that's the far left. So that's why they're called the end behavior, because the far left and the far right are the ends of the graph. So the left end and the right end. Okay, anyway, all we have to do in these problems is we would have rational functions. So we have these special ones here. And again, we could always use a calculator, or we could at least double check with a calculator. But when a limit's going to plus or minus infinity, so these are very special cases, all we have to do is divide the leading terms and then do the limit. Okay, so these are all special cases because they're all going to an infinity or a negative infinity. Okay, so we don't do this rule on like these problems from previous videos. So these are numbers like x goes to 4, x goes to 10. So we do the methods that we did on these to get those answers. Okay, so this, again, infinity is special. We have a different technique to do it. All right, so let's see what happens. So all we have to do, so we see, oh, x goes to infinity. That means all I have to do is divide the leading terms first. So this becomes the limit as x goes to infinity. And then I'm just rewriting just the leading terms. And then we can see, oh, that simplifies. So the 3 and the 15, those are each divisible by 3. Okay, so we could divide each of those by 3. And then x cubed divided by x cubed is the same thing. So those would just cancel and make 1. Okay, so that, or you could just cross it out. And then I can rewrite this as the limit as x goes to infinity. 3 and 15 each divided by 3, so we would have 1 over 5. And then we see, oh, there's no other x in this expression anymore. So that means this is just the final answer. If I don't have anywhere to plug in the x, that means we're done. So I have nowhere to plug this in. There's no x. So that means just the leftover number is the final answer. So I'm doing the limit. There we go. It's done. 1/5. Okay, and if we wanted to, we could plug this into a calculator and just look at the far right and see what the number becomes as the y-coordinate. It would become 1/5, or in a calculator, it'd probably be 0.2, so as the decimal. Okay, so that's a way to double check. Okay, so we have a nice trick to these with infinity. The reason we can do this is because when something gets super large, so infinity is like plugging in a super big number. So if I plug a super big number right into that x and cube it, that'd be a really, really big number. And then these kind of don't do anything to it. So these are small compared to infinity. Small compared. So that's why we can kind of just get rid of them. Okay, so they're not going to really do much. Okay, and then let's see how these other two work. Okay, so this is also going to an infinity, so either positive or negative. Still, because it's an infinity, I could say, well, our special method is to divide the leading terms of our numerator with the denominator. So I'd have the limit as x goes to negative infinity of 2x to the 7th over 4x to the 5th. Just like before, we can start to simplify. So 2 and 4 reduce. They are each divisible by 2. We'll show the little division by 2. And then the x to the 7th and the x to the 5th, those reduce. Remember, you have a rule with reducing bases of the same power. So if it's x to some power over x to some power, what we do is subtract the two powers to simplify. Okay, so that would become 7 minus 5 is 2. So it would become x squared. So this becomes the limit as x goes to negative infinity. So we've got divide by 2, we have 1, and then we said, oh, it should become x squared. And then 4 divided by 2 is 2. So it's 1/2 x squared that's left over. And then now we would try to plug in the negative infinity. So if I plug that in, we have 1/2, and then the negative infinity gets plugged in there. So I just set up the parentheses I did want to show. Let me put it in red. Okay, so there's the negative infinity getting plugged in. And then we'd say, well, can we do this? Well, sure, because this is going to give us an infinity answer. So when we square a negative, so squaring a negative makes the number positive. Okay, so now we would have a positive. And then when we square infinity, we would just say, oh, infinity getting squared is really just infinity anyway. Okay, so we say, oh, it's a super large number, and if a super large number gets squared, it's still a super large number. So we just write it still as infinity. Okay, so the negative squared is positive, infinity squared is just infinity. And then similar with the 1/2 times infinity, and we say, well, it's a super large number getting times by 1/2. A super large number times 1/2, we would still say is just a super large number. So still infinity. So that is our answer. So we can have infinity as an answer, or negative infinity as an answer. So it just depends on the situation. Okay, so let's see this last one. So still, it's a special case going to infinity. So I can just take the leading terms. The leading terms are the ones with the biggest powers. In case they do mix things up, they shouldn't mix things around. So be a little careful of that just in case. All right, but I have the limit as t goes to infinity, and then we're just saying, oh, it's 343t squared and 12t to the 4. And then we would try to simplify this. Okay, so let me set up limit as t goes to infinity. And they could use x, they could use t, so the letters don't matter, so as long as it's the same in the rest of the fraction. All right, and so the 343 divided by 12 actually does not reduce. That's as good as that gets. However, these reduce. Still, we can use the rule from up here, where we would say, oh, those would subtract. 2 minus 4 is negative 2. All right, so here's where, again, we have one other rule we want to use. The negative exponent, let's put that up here too. If you have a negative power, it's saying you can flip it and make the power positive in a denominator like that. So this really is 1 over t squared. Okay, so everything in the blue right here simplified to be, I'm going to put 1 as a placeholder, over t squared. And then the 343 and 12 are still in their respective spots. Okay, and I'm going to rewrite this. Let's simplify just a little bit. So the 343 times 1 is 343. And then we could say, well, this is just 12t squared. All right, so we did some simplifying, and then now let's see what happens when we plug the infinity in. So we're going to plug it into that t right there, and we're going to rewrite it. So this becomes 343 over 12 times, okay, and then infinity, and then it's still getting squared, like that. Okay, and so we can kind of follow a similar procedure that we did from the last one. Let's see what happens though. This is going to be a different answer. Okay, so I'm going to go horizontal because I might run out of room. So I have 343 up top. Infinity squared, again, we would just say is infinity. And then 12 times infinity, we would say, well, that's still just infinity. Like that. Okay, so we have 343 over infinity. Now, the placement of this infinity is what's important. This infinity was in a numerator, or to the side. This infinity is in a denominator. Okay, so if it's in a denominator, well, let's show a pattern. So we could plug in a large number too to see what would happen. But I'm just going to make a pattern over here. So if it's like 1 over 1, we know that that's 1. If I make the denominator bigger by adding a 0 to the 1, then as a decimal, it's 0.1. So 1's bigger than 0.1. If I continue this pattern, we would see, oh, it's a smaller number as the denominator gets larger. Okay, so when you have an infinity in a denominator, so what if we continue this pattern, if you threw in a whole bunch of zeros, and that's what like infinity is doing, we're just plugging in something super big, then we would have something with a whole bunch of zeros and then eventually a 1. Well, we would round this. We would say, well, this is pretty much a 0. 0 with a whole bunch of zeros, and then eventually a 1 is 0. So this whole thing just simplifies to be 0. Okay, so an infinity in a denominator gives us a final answer of 0 once it's fully simplified like that. Okay, so again, you could do these with a calculator by plugging in the function into the graph. The other way you could do these with a calculator is to plug in something large or something small. So like for number 3, just a side note, so we could let t equal, so if it's going to infinity, let t equal something with a bunch of zeros on it. Okay, so that's kind of large. And then from there, it might give you a good answer. It might show you, oh yeah, it's just going to be 0 anyway. Okay, so that's a different way to try it. Okay, but if you get used to these kind of breakdowns, I think it's a little faster than plugging the whole thing into a calculator. But it's still up to you if you have the time. It's worth it to check too. All right, that's it. Thanks for watching. If you have any questions, please let me know.